Hey, Andrew, can you hear me?
Yeah. Hey, Garrett.
That I always thought he was a Northwest person because I think we had conversations a while ago about the Northwest. And then I saw that you went to undergrad at Pullman, which is in Indiana. And so then I started to doubt everything about you. And then I realized that you did grow up in the Northwest. You just then moved there for undergrad, got a degree in chemistry, then went to UW, got a PhD in chemical engineering. You then ended up at the University of Chicago, which is where I got to know you. And Andrew has been as a postdoc and then now as a independent faculty member at the University of Rochester, kind of at the forefront on how do you take computational methods and experimental methods and use sophisticated machine learning techniques, advanced statistical techniques to merge those two things together to actually get something useful out of it. And I think the first one that really stood out to me was taking NMR information and using enhanced sampling methods in order to understand how you would actually get that underlying NMR spectroscopy, which was really novel. I'd never really thought about actually directly merging things together like that. I always take the dumb method where I calculate something and then look at the experiment and see if they line up, and if they don't, I panic. But actually feeding them back and forth into each other is, I don't know, really cool, I think. And now as an independent faculty member, he's gotten even more creative with this. And so he ended up writing a book on it and getting a career grant. So I think, I don't know, there's a lot that I'm hoping to learn from this, but then I think there's kind of a lot that we can all kind of think about how do we even push our techniques beyond the kind of standard way of hoping they line up into actually letting them feed into each other. Okay, I told you I was going to be meandering. I'm done. Let me hand it off to Andrew. I'm going to try and make it so that you're the only one that shows up in the corner, though. Okay, I think that looks good, and I'll let you take it, Andrew.
Great. Thank you so much for having me. I'm really excited to talk about some work we've been doing. So I would say since about this spring in 2021, we've really been going a lot deeper into AI. And one of the things we found along the way is that there is not really very good tools to interpret what we get from AI. And what Garrick mentioned before is one of the methods that we've been working on was using physics-based methods like molecular dynamics to gain insight from experimental data. And then we would use machine learning as sort of the glue. And I'll talk a little bit about that today, but I also want to talk about how do we gain sort of chemical intuition or chemical knowledge from deep learning? Because I think it has a real reputation of being a black box method and that there's not a lot to learn from it. But hopefully I'll convince you today that there is some understanding to be gained from deep learning. And thank you for joining me on Mexican Independence Day and the end of Yom Kippur. So this is my group, the White Lab. I want to, recognize all the students that contributed to this work, especially you, who did the first project I'll mention today, and then Gimi, who's over here, did a lot of the interpretable machine learning work, and then thanks to our funding sources here. So I'm going to give you like a real shotgun introduction to deep learning, because I think there's a lot of exciting stuff to talk about applying deep learning to. If you want to learn about the fundamentals, I've written a book on it, which is free and open source and available here. And it has lots of executable code and equations all in a nice format. And I teach a class on it right now. But so deep learning, right? So fundamentally what deep learning is about is connecting features, which we usually denote as X, to labels, which we denote as Y. So we have some features and we want to connect them to Y. And so we fit a function, and we usually call this function f hat. And this function can predict what Y is. So anywhere that you have observations and you want to connect them to some kind of attribute, we can use deep learning. And the label Y here is very abstract. Sometimes people use the probability of X so that there doesn't need to be a quote label, just how often X occurs. And that leads to some really interesting work that I'll talk about later, which is called generative methods, which allow you to generate new examples of X. So X could be a molecule, X could be a trajectory, or X could be, a text, and you can generate novel occurrences of it. So fundamentally in machine learning, sort of the workhorse of deep learning is this equation here, which is the equation for a dense neural network. And so what happens is that we have some trainable weights W that are multiplied by our features stacked into a matrix X. Then we add a bias and we put it through a nonlinear function sigma, and what comes out is our prediction for Y. And it turns out that this simple formula, if you just change the shapes of W and B, and you change what sigma is, you can construct a very large sort of neural network, we call it, which is essentially a bunch of compositions of the equation I showed you before. So at the beginning, we put in an image in this case, and at the end, we put out, this is one for, I think, drawing bounding boxes around images. So like if we have an image and we want to see where the faces are, this would identify where the faces are. So I know that a lot of people like to present neural networks as sort of like an approximation of the human brain. I think that's a bunch of garbage and just confuses students. Neural networks are just a series of functions that are mostly linear algebra. I mean, in fact, if it wasn't for this sigma term here, it would just be linear algebra. But we put this little nonlinearity, and that's what gives us this a theorem that says a neural network can approximate any function universally, provided that you have enough trainable parameters. All right, that's deep learning. There's a lot more details to it, but hopefully that gives us enough to appreciate the talk if you don't know much about it. So really, what is the science of deep learning, or what is it that we need to accomplish in deep learning? So a lot of what goes into deep learning is what I call, and some call, inductive biases. So inductive biases are explicit choices that are made in your architecture that reflect how your data came about. And this is a sort of broad term that came out from a paper by Peter Battaglia at DeepMind. And essentially they were talking about using deep learning to represent mostly social science things like relationships between people or images. But really, inductive biases for us in physics and chemistry and materials, it's about the underlying physics that generated the data. And so I'll talk to you a little bit about inductive biases that we see for things like a point cloud. So the point cloud here could be a crystal structure, or it could be a trajectory, it could be just 3D coordinates of a molecule, and then a molecular graph. So a graph obviously can be something more general, and I'll show you a generalization of a molecular graph. So something beyond just the molecular graph that you would think of from your Lewis dot structure. So maybe you've never really thought about this too hard, but by choosing to represent data as a molecular graph or a point cloud, we're making some inductive biases about it. So one of them is that if we change the order of atoms, that is, if we have integers on these atoms, like this is 1, 2, 3, if we change that order, it shouldn't change the underlying graph, so that the graph should be equivariant as we permute things. And on the other sides here on the point cloud, one example is rotation equivariance. That is, if we rotate a molecule, it shouldn't change the chemistry. Now, it's equivariance, which means that if you rotate the molecule, for example, its dipole moment will also rotate. But the way that the dipole moment should rotate should be the same as the rotation. So we're not saying that it's insensitive to rotations. We're saying that rotations should behave in an equivariant way. And I'll get a little bit more into what this means. So let's first of all dig into something called atom permutation equivariance, which is a property we'll look at in a minute. But essentially, if I represent a molecule here on the right, so this is how you turn a molecule into a format appropriate for deep learning, is that I've written out each atom in this molecule as a row vector. And I use a 1 on the C column to indicate it's a carbon, and a 0 on the oxygen column to indicate it's not an oxygen. So we call these things one-hot vectors because an atom can only be one element at a time, so it's one-hot. And on the right, I'm just showing some property that will predict. So it could be partial charge, it could be what the bond distance is between it and its neighbor. And atom permutation equivariance says if I change the order of the atoms, it also changes the output function that we're predicting, the f hat. So that's atom permutation equivariance. And although this seems pretty obvious, if you were to take this matrix and put it directly into the dense layer I showed you before, it would not be permutation equivariant because matrix multiplication is not row permutation equivariant. Then it's just sort of getting into something more along the lines of molecular dynamics. If we have a molecule like a polymer shown here on the left, I'm showing you its principal components in orange here, red, I don't know what color that is. And you can see that as the molecule rotates or translates, my principal components also rotate and translate. And this is something which is, it's equivariant. That is, if I translate the molecule to the right, the principal components translate to the right. And that's another example of an inductive bias. These are things which we know ahead of time should be true, and we can bake them into our neural network that we construct. So something that people have just sort of explored, like this was really ad hoc in the old days. And so there have been many papers on how to treat this problem. So probably the most classic approach is what are called molecular descriptors. So if you look at a molecule and instead of trying to look at the graph, you look at attributes of the molecular graph, like how many hydrogen bond donors does it have? How many rings does it have? These are things which are invariant to the atom indices or the bond indices. So these are things which are invariant to everything. And then now, you might be thinking, well, invariant, why can't we do invariances every time? What's the difference between an invariance and an equivariance? If we want to predict a per atom quantity, like we want to tell you what the partial charge is, then knowing the number of rings is not a valid approach, because if you just know the number of rings, there's no way to get out something that's a per atom quantity. So that's where the equivariance is coming. But you'll see sort of the standard methods that have been used in a lot of deep learning for chemistry, they're all invariant. And it's not really until recently we've really sort of had the power of equivariances. So, just as an example, if many of you have heard of AlphaFold, which is the new protein folding neural network, that is all built on equivariant neural network layers. But if you look back a couple of years ago, even today, like you look at what's being done in quantum machine learning, which is like a funny term for using machine learning and quantum mechanics, people do a lot of matrix determinants, a lot of pairwise vectors and pairwise distances, and these are things which give you invariances, which means if you want to predict something about the wave function that is actually spatial, you won't be able to get it with those methods. So you can read in my book more about the kinds of ways to deal with equivariances and how we can come up with these inductive biases that allow us to design these neural networks to solve interesting problems. So the methods that you should use, keeping in mind these equivariances that we want to have, or these inductive biases. If we're working with what is called the 1D representation of a molecule, which is its SMILES string, or the name of the molecule, or IUPAC, or what's it called? Not IUPAC, INCI. Then we need to use what are called these sequence networks. So like a convolution, a recurrent neural network, or a transformer. These are things which have the right equivariances to deal with strings that the 1D representation. If we're working with molecular graphs, there's a very rich theory of machine learning and deep learning on graph neural networks. Graph neural networks are really the only appropriate approach to use with molecular graphs. So if you're working with this two-dimensional representation of a molecule, we use graph neural networks. And finally, for the 3D, it's really just recently the equivariant neural networks have matured. I wrote a chapter in my textbook about it in 2020, and basically the conclusion of the textbook chapter was these methods look promising, but they're bad, or they're not bad. They haven't beaten state of the art, and they're poor implementations. And honestly, I just updated it. Like now, every state of the art method for any kind of point cloud prediction task is equivariant neural networks, and they have very mature implementations. And AlphaFold is equivariant neural network. And there was a paper that came out a couple of weeks ago on Anequip, which is a force field from an equivariant neural network, and it is state of the art. And what's really powerful about these inductive biases is that they're very data efficient. The more you can pack into inductive biases, that is, the more you know about the physics of your system, the more data efficient they become. So we're talking about, for these equivariant neural networks, only requires 50 training examples to make a state-of-the-art force field. And I think that deep learning has a reputation of something which takes millions or hundreds of thousands of examples, but no, we're down to 50 examples now, and we can have a very good neural network. So maybe you thought about training a force field from DFT, and you thought that, I would need 100,000 DFT calculations to make a good force field. No, we're down to 50. So really, we've had a lot of exciting breakthroughs lately. Just sort of a little bit of like, if you're ever treating things that you don't need to know the 3D spatial structure, or you don't need to be atom permutation of equivariant, like if you just want to predict if a molecule will dissolve in water, you should always work with the simplest representation you can. And part of the reason why is that computers have gotten so fast that you can do incredible things with 1D representation just so efficiently. So I'm going to show you an example is that over the summer, I've had some fun and made a lot of interesting deep learning tools that are built in JavaScript so that they can just be run on a web browser. And the one I'll show you right now, this is called Molecular Dream. You can find it on my Twitter or on my GitHub profile. And basically, 3 years ago, one of the big open questions was, could we design molecules, purely from hallucinations from an AI? Can an AI design a molecule that's novel? And people were working, on this problem 3 years ago, building these very sophisticated models, and they had to run on a GPU or multiple GPUs. And people were being able to generate like 20% of the molecules were real molecules. I wrote this up in a web browser in like an afternoon, and it can generate a molecule just by banging on the keyboard. So you just bang on the keyboard, and every molecule that comes out is a real valid molecule with satisfied valencies and everything like that. And I made this because my son, he likes to bang on the keyboard, and he's 2 years old, so that was his hobby. But he's really falling behind in organic chemistry. And so I thought that this would be a way for him to, be able to do a little bit more in organic chemistry while also, practicing his hobby. And he loves it. And just for fun here, if you click the red button to synthesize it, it goes to an AI retrosynthesis predictor that shows you how to synthesize that particular molecule. So this was like fun. Like maybe this isn't fun for everybody, but this is just something I whipped up in honestly like maybe 6 hours, on a couple evenings 1 week. And it's pretty incredible how advanced that these AI methods are, that I can just do this, easily, and it runs in a web browser. So kind of like along the lines of what Garrick was mentioning, I want to talk a little bit about how we can connect experimental data with simulations. And one way is in what we call a forward model. And a forward model is something like if you go from the XYZ coordinates of a molecule, you can predict a property. And then you go in the lab and you measure that property. And to go backwards, you need a backwards model. And that's where you use something like molecular dynamics or Bayesian inference. But that initial forward model going from the XYZ coordinates, the spatial coordinates of your molecule, to the predicted experimental property, that's a great opportunity for machine learning. And chemical shift prediction is a classic problem that has been using neural networks for many years. And we wanted to see how graph neural networks would do in this problem. Now, thinking about our inductive biases again, chemical shift is a per atom quantity, so we couldn't use a 1D representation here. We need that permutation equivariance because we're trying to predict per atom quantities. But we have kind of a wrinkle here, is that we need to have position-dependent chemical shift. We can't just work with a molecular graph. So what I'm going to show you is kind of a hybrid, maybe 2.5D representation, is we can build a graph where the edges are not only the covalent bonds, but the edges in the graph are also the distance vectors between atoms. And so what does this look like? So here is an example for a protein. The green atoms are the atoms I want to predict the chemical shift for. And then the gray is carbon, white is hydrogen, red is oxygen. And in here, you can sort of see the normal covalent bonds that join these atoms, but I've also drawn vectors to their nearest neighbors to build this kind of augmented graph that includes both spatial connections and chemistry connections. And this has all the properties we want. It's position dependent, it's permutation equivariant, and it's actually rotation invariant. And what's interesting about this is that I don't think chemical shift should matter if you rotate the molecule. Now, and if any of you do NMR, you're thinking to yourself, well, actually, I have to spin my samples to get good NMR. I don't mean like that kind of rotation. I mean that if you imagine, a protein and it's rotated, 30 degrees this way versus 30 degrees that way, it shouldn't matter what your chemical shift prediction is because it's an ensemble measurement. So this 2.5D representation is really effective for that. So I'm going to teach you now what a graph neural network is. Okay, start your 2-minute timer here. So in a graph neural network, the input is a graph and the output is a graph. Now you may be thinking to yourself, well, we're trying to predict chemical shifts, so the output shouldn't be a graph. Well, what we do is the input is a graph and the output is a graph, but what we just do is we throw away the edges and we only keep the node information, and that's our final prediction. But let's see how we transform a graph coming in and going out. So look at the oxygen. So what we're going to do is we're going to update our graph. So imagine that this is the input graph and we're going to update it to compute the output one atom at a time. So we look at this oxygen, it's our center. And I'm showing you again with these one-hot vectors, the oxygen. So the top number in the vector indicates if it's a hydrogen, the middle number indicates if it's an oxygen, and the bottom number indicates if it's a carbon. So my oxygen starts off with a 0, 1, 0. Because it's an oxygen. And then its neighbor is a 1, 0, 0 because it's a hydrogen, its other neighbor is a 0, 0, 1. Then what I'm going to do is I'm going to have them pass information among one another. So this hydrogen is going to use the graph to know who its neighbors are, and the hydrogen is going to tell the oxygen information about it. So you can think about it, the oxygen says, hey, neighbor, send me your vector. And then it's going to ask the carbon, hey, neighbor, send me your vector. And then it's just going to add the vectors together. And I'll show you a movie of this, but you can sort of see how that the oxygen learns that it's connected to a carbon, and then it'll do another round. And then the oxygen will learn that it's connected to a carbon, which is connected to the 3 hydrogens. And you can almost think about this as like, typing. If anybody has worked with a force field, when you type atoms, you look at who they're bonded with and who their neighbors are bonded with. It's just like that, but in a trainable way. And so let's watch the little movie here. So the left side is showing the input, and then the right side is showing the output. So you can see that as we go through this process, the atoms gain information about their neighbors. And then now it's going through another layer. So now the oxygen, you can see the oxygen vector has information about the hydrogens near it, the oxygens near it, and the carbons near it. Now, one of the things that's missing from this example is there's no trainable weights. In a real neural network, we have trainable weights so that we don't just pass the vector between the atoms. We multiply it by a weight vector that tells you what's important. Like maybe it's more important what the carbon identity is, or maybe it's more important what the hydrogen is. And then of course, the edge is also a factor in our neural network. So putting it all together, those message passing neural network layers, they sit kind of here in this dashed line in our neural network. And then we have a couple other, little details that I won't really get into, but basically remember that we have information about if it's a covalent bond or if it's a distance bond, and that kind of information needs to be converted to a vector. We also have things like, how do we convert an element identity into a larger vector? Because we don't usually work in, we don't have 8 dimensions in these neural networks. We have like 1,000 dimensions in these neural networks. So we need to sort of blow up the dimension from just a 1 for carbon, a 1 for oxygen, or something like that into a much bigger dimensionality. That's called embedding. So just, a little bit of numbers. So we trained this graph neural network on about 2,000 proteins, a small number of metabolite molecules, because we wanted to be able to predict protein ligand binding with our NMR. This came out to be 5 million chemical shifts. And this is just a little bit about how deep the neural network is, how wide the neural network is, and how we trained it. So just getting into, just the raw data, I won't go too deep into the slide, but basically, our model is here. It has about a 0.781 correlation coefficient for protons, and then about a 0.88 correlation coefficient for a specific kind of protons and on proteins. And we explored a few other methods, competing methods, but what's really, this method, what's powerful about it is that it's position dependent. Most other methods required you to know a priori what are the features, like you needed to put in the dihedral angles, or you needed to put in what residue is. Our method can work on glycosylated proteins, it can work on amidated proteins, it can work on small molecules, it can work on polymers, it can work on anything because the input is just fundamentally what are the elements and what is the distance between them. Whereas all the other competing methods require things like a bioinformatics database, or they require features that are engineered. So I won't get too much into that, but I do want to mention one interesting point we found out is that we wanted to see what's called an ablation, what mattered for the neural network. So our correlation coefficient across all element types, so not just hydrogen, across carbon, nitrogen, carbon, nitrogen, hydrogen, we had a 0.993 correlation coefficient. If you remove the distance information, so if you just say who my neighbors are, who my spatial neighbors are, you get about a 0.991 correlation coefficient, which is quite good. If we only then just say who our chemically bonded neighbors are in their distance, we're about 0.96. So a lot of information is lost there. Now you may be looking at these points and thinking, how can you possibly have a 0.99 correlation coefficient here? We're zoomed in on one region from 0 to 10 parts per million. Obviously, the nitrogen chemical shifts are much higher. The carbon ones are much higher. And also we're looking at, I think these plots are for about 50,000 points. So it's kind of hard to have a sense of correlation coefficients with 50,000 points just looking at it like this. And then one of the questions is, label variance. That is, are NMR measurements repeatable? So if you go out in the lab and you measure a protein with NMR once, and then you go the next day with it and measure it again, the correlation coefficient is close to 1, rounded to 4 decimal points for carbon, nitrogen, oxygen. If you just focus on the hydrogen, the alpha hydrogens, it's about 0.96. So then here's the full correlation. This is the focusing just on the protons. And then this is looking at small molecules. So it can work on carbon, nitrogen, oxygen. It can work on small molecules and proteins. And the reason we built this model really is that, we wanted to do molecular dynamics with an NMR model to identify salt bridging and non-covalent interactions for self-assembly. But all the existing NMR models, they weren't sensitive to non-bonded interactions. And so at the end of it, we're able to see, are we sensitive to hydrogen bonding? And this neural network is sensitive to hydrogen bonding. So I have in dash green, there's some experimental measurements on how much a chemical shift you get for a hydrogen bond. And then in orange, that's what our neural network predicts for the hydrogen bonding chemical shift. And this is just some secondary structure information. So I think it was a really cool and successful project, but what's really the most rewarding thing about this is that we have it up on Python. You can do pip install nmr-gnn and put in a PDB file. You can put in a GROW file. You can put in a mol file, anything that you can get into MD analysis, which now has RDKit integration. You can get the chemical shifts in one line of Python, or sorry, this isn't even Python. This is just the command line. So just one line, and you can get the chemical shifts. And here I'm doing a stride. So this is over a whole trajectory. So an MD trajectory, getting the chemical shifts for every single frame. And it runs like, I think it's like 1 million chemical shifts per second or 6 million per second. It's very efficient. And we put some emojis in it so you feel fun when you're doing. Okay, so that's one example. We've written a lot of papers, and there's lots of papers out there on using graph neural networks to predict molecular properties. And also there's a lot of papers out there for just, doing deep learning and chemistry. But one of the problems is that we kind of want an explanation for why we're doing this. And it's easy to say, of course, we want to, at the end of the day, have chemical intuition, but it goes beyond just chemical intuition. So in Europe right now, they actually have some laws about if you have a commercially deployed AI or machine learning method that makes predictions that affect people, it has to offer explanations. And then the G8 or G7, I forget how many people are in it now, they released sort of a draft statement a couple of years ago saying that AI should be explainable and that people should be entitled to an explanation for AI methods that affect their lives. And I think this is really important in chemistry because we have something that says, test this molecule, or this molecule we think would be good for treating this disease, or do animal research with this molecule. You have to have an explanation. Like, nobody is going to just believe these things, especially with the kind of garbage that can be put out. And so I think explainability in chemical AI is something that's really missing in the field. And so we came out with a paper a couple of weeks ago about using a method called counterfactuals. And I think this is really important for doing deep learning in chemistry. So before we get too far, I need to do some definitions. So we can't make a neural network that is interpretable. That is, you can't make a neural network that you can just look at and understand what's going on. Instead, the best we can do is have a neural network where we can explain each prediction. So we're not trying to make a global interpretation. Like, we can't say the neural network makes its decisions based on the solubility or how many nitrogens are in it. What we can do is that we can say for this particular instance, it predicted it because of, X, Y, Z. So just some details here. So justification is reasoning for using a prediction. So this could be something like how accurate the neural network is, what its test error is, what its correlation coefficient is. So justification is like, you should use it because it's so good. Interpretability is the degree to which an observer can understand the cause of a decision. So this is that first thing I said, that interpretability is how much you can just look at the model and sort of intuit what's going on. So as an example, consider linear regression. Linear regression, you can look at each coefficient and understand what's going on. And then an explanation is a presentation of information intended for humans that gives context and cause for a specific prediction. So this is what we're looking at here, is can we explain a specific prediction? You'll have probably seen feature explanations before. So sometimes people in machine learning and deep learning will say, the most important thing was like this oxygen atom here, or the most important thing was the molecular weight. And that's okay. But it's actually not a complete explanation, and it's not always understandable. Another kind of explanation you can see is a contrastive. what would the outcome be if the features were different? So rather than saying, this oxygen is the most important thing, you can say, if this oxygen were a phosphorus, this is what would happen. Or if this, that's quite a change. But maybe, if this carbon had a double bond here, what would be the difference? And then a counterfactual explanation is sort of the most, I think, complete explanation, or I should say complete, but this is sort of the best explanation we can do in instances is what is the closest set of features with a different outcome? So not just contrasting it, so not just saying what would happen if this were double bond, we're finding a small change that would give you a completely different outcome. So for example, my grant proposal was rejected from the NSF. This is a true story. If I correctly formatted my references, it would have been funded. Well, I don't know if that's a true story, but that's an example of a counterfactual. So we're in a very similar setting. The references are, the only change is that my references were correctly formatted, but it's a very different outcome that it would have been funded. Now, if this is true, like this is kind of a complete explanation. My NSF grant was rejected because my references weren't formatted. But what we have done is we've kind of set up a recipe for how to find that explanation by constructing a counterfactual. So what does this mean in chemistry, right? We're talking about counterfactuals for a while. So in chemistry, here's a molecule on the left, which is predicted to not cross the blood-brain barrier. And on the right, I have the smallest possible change so that it does cross the blood-brain barrier. And you can see that, that adding this this ester will change the property. So you might think that the carboxyl anion is what's responsible for preventing it from crossing the blood-brain barrier because just to adding an ester makes it cross it. So this is an example of what a counterfactual looks like in chemistry and why it can be important. Now, one thing to remember is that I'm not trying to explain why molecules cross the blood-brain barrier. I'm explaining why my AI that I trained predicts things cross the blood-brain barrier. So although in principle, if my model can perfectly represent crossing the blood-brain barrier, these explanations have something to do with the biophysics of it. But we're not after that right now. We're not judging it based on if it does a good job of predictive biology. We're judging it based on if it can explain my neural network. So just getting a little bit more specific, a counterfactual is a solution to an optimization problem. Given a prediction f hat of x, find a x prime, which is as close as possible to the original set of features x, but it has a different outcome. Now, the reason why our paper that came out a couple of weeks ago has been very exciting is that in the past, this has been very difficult because you need to do optimization here and you need to do optimization over a molecular structure. If anybody has ever tried to do gradient descent on a molecular structure, you'll realize that's it doesn't make any sense, right? But there was a method that came out in, I think, May or something called Stoned that allows us to efficiently enumerate chemical space around a target molecule. So on the top left is like my instance that I want to predict for. And what I'm showing in the animation is a whole bunch of changes to that molecule. And Stoned is a very efficient way to explore chemical space. So the way our method works is that we start with a base molecule for which we have a prediction. And then we expand chemical space around that prediction using this method. So, I'm showing you a bunch of different molecules and I'm doing like a PCA projection so that it fits into 2 dimensions. And then we identify the most similar molecule with a changed label. So the yellow and the purple, the yellow is the change in the class and the purple is the same class as the base molecule. So you see this yellow dot identified here. This is the one that has the change in outcome, but it's as close as possible to the original. And then we do just a substructure comparison and you see the red, it shows that I deleted the carboxylic acid, and that was enough to change the outcome. And so then the counterfactual explanation is that carboxylic acid is very important for the property. Here's just a specific example for blood-brain barrier crossing. So the base molecule is on the left, and I'm showing you some different changes to make from it. We do some fancy stuff like to come up with multiple counterfactuals, we do a dimensionality reduction clustering search so that we don't just propose the same counterfactual with slight changes to it. We try to get some diversity in it. Now, the accuracy of this method, accuracy here is a relative term, so maybe I would say the usefulness of this method depends on our ability to generate close interpretable structures. So the Stoned method has been really great for us because it works generally. It doesn't require training or anything like that. But another method that you can use is you can just look up in a database, what are similar molecules to my current molecule? This works for if you have a database. So PubChem is like drug-like molecules. So you can use PubChem as a way to generate counterfactuals if you're working in drug design space. But if you're working with something that has nothing to do with drug molecules, like if you're working with, organometallic chemistry, then this wouldn't be applicable. But one of sort of the important not breakthroughs, but one of the important changes we had to make was that the stoned method is very good at generating lots of molecules. But there are some molecules that we think are not like human interpretable. So for example, on the far right here, my counterfactual is that if I remove one electron, I'll have a very structurally similar molecule with a different outcome by just removing an electron. But I mean, that doesn't really help me understand what's going on in the system. Removing one electron is useless, I think. And then also similarly, like adding a positively charged mercury is a small change, but gives you a very different outcome. So what we did is we had to think about how to modify this method so that we only generate what we would consider human interpretable or plausible molecules. And that's kind of a subjective thing, but at the end of the day, what we're doing is trying to understand an AI model in a way for humans to understand. So I think it's a fair thing to do to try to make them human interpretable. So again, just do pip install xmol, and this method is completely black box, generic. It needs to know nothing about your model. All you need to do is give it a callable function, and it will explain the predictions. So it doesn't just have to work on AI methods. You could use this for a quantum mechanics predictor. You could use this for a classical molecular descriptor-based approach. You can even use it for molecular dynamics. We're kind of excited about this method. And so, this is the amount of code it takes to run this. So it's a very approachable method. Now, I want to just now talk about sort of a continuation of this work, is that we got this to work. I think this paper came out in early August, and there was a lot of excitement, and we talked to some chemists in industry that do machine learning. But one of the things they kept asking about is they wanted to know, like, in our counterfactual explanations, how important was solubility, or how important was the number of acid groups or the pKa? So we decided to go a little bit farther and also include information about these properties. But this requires a very different approach. And the reason why is that if you tell me, make a new molecule with a solubility that's 0.5 units higher, that's not really possible. You can only generate similar compounds. So what we did instead is we used a surrogate method. And so this kind of is like, counterfactuals are fundamental. I talked to this professor from philosophy about explanations, and counterfactuals have been deemed by philosophers to be like, in the handbook of philosophy, it's basically one of the major branches of explanations. And even you might think like, my exposure to philosophy is like watching The Matrix. So like, I know causality. But it turns out causality is a subfield of counterfactuals. So counterfactuals are actually a pretty fundamental method of explanation. But ultimately, I think counterfactuals, although they're a complete explanation, they are fundamentally true. A lot of times they're not practical because we kind of want something a little bit more, I would say something that we can act on. Like knowing solubility is important, gives me something which I can think about as a chemist. Maybe a counterfactual explanation saying if this ring weren't here, it would work. That's maybe not as useful. So we have been working on another method, which we call, where we build a local surrogate model. So we construct a model around the space of our deep learning prediction, but we make sure that model is interpretable. Now you might be thinking, if you can fit an interpretable model to your AI, why not just throw your AI out in the garbage and just keep the interpretable model? Well, the interpretable model can't be fit everywhere. We're just going to fit the interpretable model locally around our base molecule where we're doing the prediction. So we just do a linear regression, center that regressed fit around the molecule of interest, the thing we're trying to explain, and then we can see what descriptors matter. So did solubility matter? Did number of hydrogen bonds matter? So I have a little lime or lemon emoji because this method is called lime, but due to reasons beyond my control, the UTF-8 committee has not approved a lime emoji yet. So we're working with lemon right now. So the question is, how do you explain a linear regress model? So for those of you who don't know, to explain a linear regress model, we use what are called t-statistics. I don't really get into this, but basically the trick of like, how do we make the model fit locally is that it's a weighted least squares regression where the weight is how similar it is to the base molecule. So thinking back to our space, right? I have like my base molecules over here on the left, and the label, like the Y in my regression is the color, and I'm trying to fit according to distance. So I want to fit these colors, but I weight them by how close they are to my base. So these like yellow ones here in the far right are very unimportant, and the ones to the far left are very important. Now, what descriptors? So that's really the key is what descriptors can you use? So this is kind of a circular question because, like, for example, I think solubility is a great descriptor, but there is no way to compute solubility from a structure generally. Like the best way to do it is to use a neural network, which is like what we're trying to explain. I haven't resolved the philosophy of that one, but so what we do is we use what are called classical descriptors. So instead of solubility, we use predicted log p. And then we use something called max keys. Max keys are basically some company in the 80s wanted to store molecules in a database, and then they wanted to search against the database to find molecules similar to ones they have. And so they wrote down a bunch of questions about a molecule. And those questions are things like, does it have an oxygen? Does it have an aromatic group? Does it have an amide? And these questions were turned into like little computer programs to evaluate them. And so we use those 160 questions about molecules as descriptors. This list 1, 2, 3, 4. This is not exhaustive. We use more than this, but just those are 4 examples of descriptors we use. So then we want to know, like, why is this molecule on the right have a solubility of whatever it has? Actually, you should probably write that down. I think it looks like it's soluble. Or sorry, it looks like it's insoluble. And then on the left here, we fit that linear regression to all the points. We did our t-statistics, and we looked at those descriptors and saw which ones are most important. Now, this one here is there an atom bonded to another atom by a ring bond and bonded to an oxygen by a chain bond? That's sort of a complicated question of saying, do you have an oxygen that's attached to a ring? And it says here, you know, a very positive to the right. So that means that if this question is true, it boosts the solubility. Is there an oxygen with at least 2 chain bonds? So it's like an ether, and that pushes it down. Now, you may be thinking, in general, adding ethers should increase your solubility. But remember, we're in the neighborhood of this molecule. We're trying to explain why this molecule has the solubility it does. And it has to do with how many molecules are, you know, I shouldn't say ether, but how many molecules have bonds that connect them. So it has to do with these epoxies. So those are sort of the max keys. We can also look at these descriptors, so molecular complexity, and then this partition coefficient, atomic polarizability, which is just basically the partial charges on it. So increasing partial charge increases solubility, and decreasing solubility, predicted solubility decreases solubility. All right, so I think this is kind of new stuff, and we're trying to fit it all together, but we're really trying to push the limits on AI, not just being predictive accurate, but also explainable. All right, the last sort of project I'd like to mention is collaborative machine learning. So one of the things that sets apart chemistry from most other disciplines is how valuable the data is. So if we go in computer science, I talk to my computer science collaborator, and they'll say things to me like, why don't you just get more data? You only have 500 data points. Can't you just get more data? I tell them, oh, it's actually kind of expensive to do a chemical experiment. For them, if they have a data set, they need to get more data. They just go on to something called the Amazon or the Mechanical Turk on Amazon, and they pay people 10 cents, an example to label images or do text classifications like that. It's very easy to get 1,000 data points for $100 or something, or $1,000, $100. So one alternative approach is to separate out like the value of the data with the machine learning. So this is an approach, this is an assumption I have, is that I think there's actually a lot of data out there in chemistry, but people don't want to share it because they think it's valuable or they want to protect intellectual property. And what we were doing in this paper is we showed a way to share the machine learning models to build a better machine learning model, like training on the data, but without sharing the underlying data. This is an approach called federated learning. And so the main idea in federated learning is that we, like a series of institutions, research groups, companies, collaborate to build like the one true model of solubility. But rather than sharing measurements they've made on solubility, and which would have to include the compounds, what they do is they share a locally trained model on solubility from their institution, and they send it out to some cloud or some server, some head node. And then that head node aggregates all of the local institutions' models of solubility into one global solubility model that's better than each of the individual ones. And so I think there's some major tasks in chemistry like pharmacokinetics, like toxicity, side effects, solubility, safety data. These are all things that would be great to share or to build collaboratively, but companies don't want to release their underlying chemical structures. And federated learning is a way around that problem. So this paper came out, like 14 hours ago? So I haven't really had time to build great slides. So just bear with me for a second. I'll try to walk us through some of the data in it. So what I'm showing you here are a few tasks that are done in deep learning. And what we've done is we've artificially split the data up into different institutions. And this parameter alpha is indicating how we split them up. So an alpha that's very high means that we split the data up uniformly, randomly between the institutions. An alpha that's low means that we did what's called a scaffold split, is that we gave each institution a certain category of molecules. Like, so maybe one institution just has, amides, or maybe one institution has a scaffold that's a bicyclic. Or maybe one institution is just working with long chain long chain molecules. So when we split the data up in this, what we call a heterogeneous setting versus homogeneous setting, traditional federated learning methods kind of fall apart. What we did in this paper is we showed that they do fall apart. That was not known. So if you just try federated learning methods from other disciplines, they don't work well. And then what we did in this paper is we recovered the performance using a method called FLIP. And so essentially, if you train, for example, let's look at QM9. So this is predicting quantum mechanical properties. If you look at all the data uniformly, you can get a prediction accuracy 0.09 EVs. Then if you go and you train it distributed using a standard method, you get about a 0.59 EV. So you have a big loss in performance. And we can recover some of it down to like 0.52 over here. That's actually not very good, but it's a hard problem. Maybe we can look over like the solubility or lipophilicity. This one here is 0.63. We can recover the performance quite well here with this method, whereas we lose a little bit in the homogeneous and heterogeneous settings. Okay, so how does the method work? So what we do is we don't just share the models among the institutions that are participating. We also include information about how well the models fit. So the server shares the current global model, and then each participating institution tries to fit their local model, but uses insight about how different their model is from the global model. So you can't just compare the models directly, like you can't just look at the weights. What you have to do is you have to measure a prediction with the global model and then your current local model, and then you can reweight where things disagree. So here, like these red points disagree between the local and the global model. And then, so those points are given more weight as we train. So I think that federated learning is actually kind of the future of deep learning in chemistry. We've done, I think, as much as we can on trying to collaborate and build large data sets. But I think sort of the next chapter in deep learning is about collaborating on models rather than collaborating with data, just because, although I hope that chemistry becomes more automated and data becomes cheaper, but at the end of the day, I think people just don't want to share molecular structures. And I think that's just a practical reality of IP and businesses. But I think we can move forward on deep learning through approach like federated learning. Okay, so I'm just going to mention a little bit of work we've done recently on natural language processing. So I wrote a perspective that you can find in arXiv about a new kind of deep learning method which can generate computer code from natural language. And in this picture here, you see this. This is the dimerization, or sorry, this is the energy curve for H2. So we took H2 and pulled it apart using a quantum mechanical method and measured its energy. Now, this plot like the calculation and the plotting and the axis labels and everything was generated just by me saying, compute the dissociation curve of H2 using PySCF. So the computer is able to understand what H2 is, understand what a dissociation curve is, set up the quantum calculations, execute it, and plot that. And it did it using STO3G, Hartree-Fock. So then I said, use the most accurate method, and then it came back to me and did it using couple cluster. And so it was like a dialogue with this method to generate code. So I think I have a demo here about a tool we've made that allows you to interact with this to do computational chemistry just with natural language. So the first thing I say here is, get the largest 5 folders in home. If anybody's ever tried to work on the command line interface, some things are just really hard on the command line. So get the current month, for example, is a little bit hard. And it's showing you here the code to do that. So then I say, I want to do some MD triage, so MD analysis of trajectories. And I say now load the trajectory and select the hydrophobic residues. So then it loads the trajectory, writes the code to do it, and it selects the hydrophobic residues. So it not only knows how to load a trajectory into this Python package, it also knows what a hydrophobic residue is and how to correctly select them. Now I say, let's do some PySCF quantum. And here's that example I said before, compute the dissociation curve of H2. And I hit enter. Oh, I think energy curve. I don't know how much that would matter. And you can see it actually generates the coordinates for H2. It writes a function to build it. It knows what basis set to use and things like that. Now use a more accurate method. And then now it does it with, I think it does relativistic Hartree-Fock with an exchange correlation. Functional. All right. So all this stuff you can find on our code. I post a lot about NLP. It's something that's on my mind a lot on Twitter, so you can follow me on Twitter to learn more about it. That demo I just showed, you can do pip install NLCC to run it on your own machine. And we think it's going to be interesting as a teaching tool and also a research tool, and we're trying to study it more. But read our perspective about it. We talk a lot about not just writing computer code. There's a lot of interesting applications of natural language and chemistry, like we can now do things like convert a methods section from a research paper into a recipe, or look at a paper and say, find all the solvents that were used, and it can extract them. And these are not things that you have to train. You don't have to train a neural network. You just tell it to do it. And this is kind of this idea of these large language models, which have been trained on basically all of human knowledge. They're literally trained on 1 billion documents. And they can do not just chemistry, but almost any kind of language task. I shouldn't say they can do them. They give you good baseline performance on almost any language task without training. Okay. So, what?
Good night, Walgreens.
Oh, good night. My son said good night, Walgreens. Funny names. Okay. With that, I'd like to end my presentation, and I'd be happy to take any questions.
Thank you, Andrew. I don't think Zoom translates clapping very well, but there was clapping.
Okay.
Yes, thank you. Are there any questions? Acknowledge the 2-year-old and he didn't introduce. There's an objection to you not introducing your son.
Oh, he's already gone to bed. I'm sorry. He's a constant companion of mine. I just assume, it's so funny. Whenever he sees me, he's like, "Oh, are you talking to your friends?" And yeah, I'm talking to my friends. Yeah, I have a 2-year-old and a 1-year-old, and they've been my constant companions for the last 2 years almost.
Yeah, I think we all understand that. I don't have kids, I have dogs, but I'm going to equate my dogs with your kids.
The same thing.
Joel, maybe do you want to come up here and ask your question so we can hear?
Yeah, thanks for that talk. That's really nice. I really appreciate your modern approach to solving problems. I guess you can see me here.
Yeah.
Have you had any interaction with or made any use of BOINC, Berkeley Open Interface Network Computing? It kind of has, it seems like the opposite problem where they have too much data and they need more computing resources to handle it. So I'm not sure if you run into that or not.
There's like this thing like the data deluge people talk about, like where there's too much data and we don't know how to handle it. I think to some extent, that is really important for synthetic data or a very specific type of experimental data, like something like, the particle accelerators at CERN or any particle accelerators where you just have instruments that just generate a lot of data. But I think in chemistry, in my opinion, in material science, that it's very rare that you generate so much data you can't handle it, unless it's like synthetic, like it's coming from QM or coming from MD. And I think that there has been a lot of work in the materials informatics. There's been a great materials genome project, materials genome initiative. They've done a lot of data generation, but almost all of it has come from first principles calculations. And I think that's cool. And we've done a little bit there, but in my group, we've kind of tried to focus on what I would call like medium to small data sets, which I think are more representative of chemistry and material science.
So, Andrew, in material science, as I think about access to data and the ability to extract information from it, I think of the barrier of collecting from the primary literature, where things get spread across thousands and thousands of papers that potentially are relevant to whatever question I might want to ask. Solubility, like you brought up. There are all these solubilities out there in the literature. They'll get expressed with different units and different labels. It'll be really tough for me individually to go through and capture all of those. Even writing some AI that can, comb through the literature, pick out the relevant values, make sure it gets them formatted appropriately so that you can then feed it in. I don't know, for some reason, that's where my brain goes with trying to collect data rather than these big repositories that it seemed like you were kind of referring to.
Go ahead.
I guess that's the end of it. I'm petering out, but I think there's a question there. I'm just not quite sure. How do you put all that together in order to use the literature as, something you can leverage for these sorts of AI-based explorations?
So there has been some work, and to kind of what we were discussing before is Kristen Pearson's group at Lawrence Berkeley, I think, has done this work on thermoelectric materials. And what they did is they basically went to materials and they parsed them with natural language. And they put it together in like a database of 56,000 paper analysis. And they were able to do some basic stuff like connect to similar systems, even though maybe they were described with different words, and they were able to try to predict properties of thermoelectric materials. But I think honestly that talking to people who do material science, that there's just, I don't think it's a fruitful approach because there's so much stuff that's kind of hidden, like two groups do the same material and you will get different answers, or, maybe a method section won't talk about something that's important detail. So there is an approach called like domain adaptation, where you try to account for the fact that different groups doing it or different journals or different approaches kind of are different. You try to build it on some global model. But personally, I think that the sort of forefront is small data sets where you find a few very relevant examples and use that as a way to guide what experiments you do next. And I think that there's a lot more interesting questions and science to be done in an iterative feedback loop where you query, I have these 10 data points, what's the next one to do? And then it will say, do these 5 experiments, that'll be the most valuable. So I think that, I don't know, maybe someone will crack it one day, but I think that doing a very broad exploration of many different papers and trying to parse it out into one sort of, global model that describes all of this literature, I think that's very difficult and not a fruitful direction of science.
Okay. There are a couple of people with their hands raised. I'm not sure who was first, so does someone want to jump in and ask? Go for it.
Hello, thank you for the talk. So I have a quick question. It was regarding when you were talking about the graph neural networks. It was that model where you had the oxygen, the carbon, and the hydrogens. Mm-hmm. And in that model, you had each atom or node checking its neighbor, starting from left to right. So I was wondering, is there a reason for that? Is it more optimal, or have you considered like trying from just a random position, like the center of that, and working out?
Yeah. Okay, so this is fascinating. So we actually cannot let the order of the neighbors matter, because if the order did matter, we would break permutation equivariance. So even though in my animation I show them, the way we combine the information has to be independent of the order of the neighbors. So in that example, we took the average over our neighbors. So even if we did left to right, or we started here or another spot, or we changed the order or random, it all disappears because we take an average over the neighbors. And that's actually sort of the key idea of the algorithm, is that the way we get permutation equivariance is by treating our neighbors equivariantly. That's a good question.
Thank you.
So I have kind of a question. It looked like a lot of the models that you were doing only had 3 different atoms in them. I was just wondering how complicated, how many atoms can you add into these models?
I think you mean elements, right?
Yeah, elements.
Yeah. Our protein NMR predictor, it actually works with all elements that are in the training data set. It's just that the groups only report carbon, nitrogen, and oxygen chemical shifts typically. So we just don't have enough data on any kind of other chemical shifts to be accurate. But when we take in the protein obviously has sulfur, it has phosphorus, right? So we have other elements that we consider. And then like on some of these other examples that we had, like I don't know, the XAI one, the counterfactual predictor, that one can handle any element that's in your training data set. So a lot of these things are just like, if you have it in your training data, it will appear when you do inference. So when you use your model in practice. But yeah, so to answer your question, it's basically what is in your training data determines what you can use. In specifically the graph neural networks for predicting chemical shift, it does use the full set of elements that are in the training data, but the labels were just on carbon, nitrogen, and oxygen. So that's all we predict.
Okay, thank you.
All right, Jesus, go ahead, and then I'm going to cut it off after that because we're at 5.
Okay.
But go ahead and ask your question.
Okay, thank you. So thanks, Andrew, for your talk. And I was wondering if your method could be applied for finding the chemical structure for a material having some properties such as a specific viscosity or density or some other properties. So if I fix the property, if I set up the property, do you think that your method could find the right molecule for that material?
Yeah, actually, I think there was a paper on that like 3 hours ago that came out. I saw on Twitter. Yeah, so this is so this is kind of a category of methods called conditional generative models. So we want to have something that can like hallucinate a molecule, but you want it to be conditioned on certain properties. That is definitely something that can be done. So yeah, there's kind of 2 approaches. One approach is like what I just said. So you condition, like I want things with high viscosity, generate molecules like that. Another approach is kind of like maybe optimization. Like that is, we have a method which can generate lots of molecules and we want to use it to kind of narrow in on molecules with a certain property. And that's possible too. So that's kind of just like a nomenclature thing. So rather than saying we want to generate molecules that have this range of viscosities, we want to find a molecule with a specific viscosity as like the optimization criteria. So then you can use methods like Bayesian optimization. You can build a latent space. So there's a famous paper by Rafael Gomez-Bombarelli and Alana Spiro-Guzik from 2018, where they did a variational autoencoder. So they basically went from molecular structure to a high dimensional latent space. So this is a method to turn a molecule into a vector. And then you can use continuous optimization in the vector to generate a molecule with it. So short answer, yes, there are many ways to do what you just asked, and many more being discovered every every day.
Okay.
Yeah.
Okay, thank you.
Yeah, send me an email if you want to know more specifics.
Okay, thanks.
And I think I'll echo that. If anyone has more questions, feel free to contact Andrew. I know with him not actually being here, it gives it a little bit different dynamic, but he's a nice guy. You can email him. One more time, thank you, Andrew. Really appreciate you coming and talking with us.
All right, thank you.
We have more seminars coming up, so please come back next week and for the rest of the semester. And Andrew, thank you for giving up your evening. I know it's 8 o'clock there, so thank your family, your kids. That was very generous of you. All right. Bye, Andrew.
Thanks for having me. Bye-bye.
Bye, everybody.
Thank you.